Now, let's rewind and start the whole course over. I'm only sort of joking. Let's go through all the same ideas again, but through the lens of looking at graphs. Consider first this graph that we looked at earlier, and let's imagine it's the graph of the position of an object over time. We can make the vertical axis the displacement from the starting position in meters, and the horizontal axis the amount of time elapsed in minutes. If I wanted to calculate the average velocity of the object, I could do so in the exact same way we did when we worked with this graph before. Choose two times, say 0 minutes and 2 minutes. I'm choosing two different times from the original example so that we get a bonus example here of calculating average rate of change from a graph. Look at the corresponding y-coordinates, in this case 0 and 3, respectively, and then calculate delta y over delta x is f of x2 minus f of x1 over x2 minus x1, so f of 2 minus f of 0 over 2 minutes minus 0 minutes, which equals 3 meters minus 0 meters over 2 minutes minus 0 minutes, so 3 over 2 meters per minute. What we have found is both the average velocity over the first 2 minutes and the slope of the secant line through the points 0, 0, and 2, 3. A secant line is a line through 2 points on the graph of a function. Fun fact, the word secant comes from the Latin word secare, or however you say it in Latin. I don't speak Latin, which means to cut. And while it isn't the same secant that you learned about in trigonometry, the trig function secant actually is named secant because it can be represented by a secant line on the unit circle. In both cases, the secant line looks like it's cutting the curve because it intersects it in 2 different points. What if instead of the average velocity, we wanted to use the graph to find the instantaneous velocity at a specific time? Just like we did before, we can estimate the instantaneous rate of change by calculating average rates of change over shorter and shorter intervals. We will do a specific example with calculations next, but let's just get the concept first. Let's suppose I wanted to know the instantaneous velocity of the object at 2 minutes. We could start with the average velocity from 2 minutes to 3 minutes and find the slope of the secant line through the points 2, 3 and 3, 2. Then we could make the interval smaller and look at the average velocity from 2 minutes to 2.5 minutes. And we can keep drawing secant lines where the 2 points are closer and closer together, and the slopes of these secant lines should be better and better approximations of the instantaneous velocity at 2 minutes. The natural conclusion of this process is that the instantaneous velocity will be the slope of the line where the 2 points become the same point. This line is called the tangent line to the curve at t equals 2. Tangent comes from the Latin word tangere, which means to touch. Think like the English word tangible. And it is the line that just touches the curve in the neighborhood of 2. Unlike the secant lines that intersect the curve twice, the tangent line only intersects the curve one time near the t value. Notice that it is of course possible for the tangent line to intersect the curve elsewhere, but the point is that the curve only intersects the curve once at the t-value where it was drawn. The curve sort of bends away from the tangent line on either side of the point. Another fun fact, it's also not a coincidence that one of the trig functions you learned about in trigonometry is called tangent. The tangent's value is directly related to a tangent line to the unit circle. Tangent lines are incredibly important in this course, to the point where if you learn nothing else, I want you to leave knowing this. The slope of the tangent line is the instantaneous rate of change in the function at that point, which we will define to be the derivative of the function at that point.